All right, let's talk about one of the coolest, most interesting pieces of silicon on the planet, the Field Programmable Gate Array. You'll hear it called an FPGA. Today, we're going to break down exactly what these chameleon-like chips are, why they're so important, and why the biggest names in tech are betting billions on them.
So, start with this question. What if a computer chip wasn't, well, permanent? What if it could completely rewire itself, long after it left the factory, to become whatever you needed it to be, right here, right now? That's the wild idea at the heart of the FPGA. Now, to really get what makes an FPGA so special, you first have to understand its polar opposite. See, it's really a story of two totally different philosophies for building a custom chip.
Okay, first up, the star of the show, the FPGA. The name kind of gives the game away. It's an array of logic gates that's field programmable, which just means you can program it out in the real world after it's been made. The Lego analogy is honestly perfect. You get this giant box of versatile, standard blocks, and one day you build a race car, the next day you can take it apart and build a spaceship. It's all about flexibility.
And then you have this guy, the ASIC, the application-specific integrated circuit. This chip is designed from day one to do one single thing, and that's it. It will never change. Think of it like a custom-molded part for a model airplane. It's the perfect shape for a wing, it's super efficient, and you can stamp out millions of them for next to nothing. But it will never, ever be anything but that wing.
So this is the fundamental choice engineers have to make. Do you go for the endless flexibility of the FPGA or the laser-focused specialization of the ASIC? And believe me, that choice leads to some major trade-offs when it comes to speed, cost, and how fast you can get your product out the door. Let's get into the showdown.
First round, speed to market. This is a knockout for the FPGA. I mean, it's not even a contest. You buy an off-the-shelf chip, you load your design onto it, and you're basically done. With an ASIC, you're starting a long, complicated journey of design, testing, and fabrication that can easily take a year or even longer. In the tech industry, a year is an eternity. Next up, let's talk about money. With an FPGA, the upfront cost is, well, just the cost of the chip. There are no non-recurring engineering costs, or NRE. An ASIC, on the other hand, has absolutely massive NRE costs. We're talking millions of dollars just to design it and create the manufacturing masks. But, and this is a huge but, once you're in mass production, the cost for each individual ASIC is incredibly low, while each FPGA chip stays relatively expensive.
And this quote from an engineer just nails it. It's all about volume. If you're building, say, the next big smartphone, and you know you're going to ship 100 million of them, then suddenly those huge upfront ASIC costs don't look so bad. Spread out over all those units, the cost per chip is tiny. For mass market electronics, the ASIC is king of cost.
But what about raw performance and power? Again, this is where the custom-built ASIC really shines. Since every single transistor is laid out perfectly for one job, it's insanely fast and sips power. An FPGA, with all its general-purpose, reconfigurable wiring, just can't keep up. It's a bit slower and a lot thirstier for power. You know, you can't have a phone that dies after one 10-minute video call. So, to wrap up the showdown, at the end of the day, if you need the absolute fastest speeds, the lowest possible power, and you're going to make millions of something, the ASIC is your champion, no question. But for just about everything else, for prototyping, for products with smaller production runs, or for things that might need to be updated in the future, the FPGA's incredible versatility wins out.
Okay, so how do you actually tell one of these chameleon chips what to be? This part's really interesting, because you don't program an FPGA like you program a computer. It's a totally different mindset. This is probably the most important concept to get your head around. When you're working with an FPGA, you're not writing a list of instructions for a processor to follow one by one. No, instead, you're using a special language, an HDL, to literally describe a physical electronic circuit. You're describing what gates you want and exactly how they should be wired together. You are designing hardware with text. And this is the process that turns that text into reality. It starts with your design, your description. Then a process called synthesis translates that into a circuit. Then the tools figure out the best way to place and route that circuit using the FPGA's available resources. The final result of all this is a single binary file. We call it a bit stream. That bit stream is the magic file you load onto the chip to make it become your custom design. And if we zoom in on that synthesis step, this is where the real translation happens. The software tools read your code and start building. They see a plus sign in your code and substitute in an actual circuit for an adder. They're smart enough to infer what you're trying to build from the patterns in your logic. And then it optimizes the whole thing, simplifying the logic to make it as small and fast as possible.
You know, back in the day, this whole flow was pretty simple. You had one team, one design, one chip. But look at the modern workflow on the right. Whoa, it's a whole ecosystem now. You've got teams buying pre-made functional blocks, we call that IP, from third-party companies. You've got system integrators piecing it all together. And all this complexity, well, it opens up a whole new can of worms, especially when it comes to security. All right, so we know what they are, we know how they work. Where are you actually going to find these things? The answer is pretty much anywhere you need a combination of high performance and the ability to adapt. FPGAs are the secret ingredient powering so much of our world. Huge data centers from Microsoft and Amazon use them to accelerate things like search algorithms and AI workloads. They are the absolute backbone of our 5G cell networks. They're in advanced military radar, in the medical scanners that create CT and MRI images, and they're becoming critical in cars for processing data from things like LiDAR sensors. And of course, before you spend millions on an ASIC, you build and test your design on an FPGA first. They are really at the cutting edge of, well, everything. Which brings us to the future. Because of all this, because they're so powerful and versatile, FPGAs are now at the very center of the tech industry's biggest, most strategic chess moves. Look, when you see a company like Intel spend $16 billion to buy Altera, and then their main rival AMD turns around and spends $49 billion to buy Xilinx, you know something huge is going on. They're making a massive bet that the future of computing, especially in the data center and for AI, isn't just about faster processors. It's about hardware that can adapt and reconfigure itself on the fly. It's not just a feature anymore, it's a necessity. But with great value comes great risk. The very thing that makes FPGA so amazing, their flexibility, also makes them a huge target. And this chart shows a pretty shocking result of that. Back in 2017, programmable chips like FPGAs were the single most counterfeited type of electronic component. Why? Because they're valuable, and there's a massive black market for stolen designs and intellectual property.
And it all comes down to protecting that bit stream, that file that holds the entire design. As you can see here, that bit stream is vulnerable at every single point in its life cycle. From the moment it's created on a designer's computer, to when it's being sent to the factory, to when it's running out in the field. An attacker could steal it, copy your design, or even worse, sneak in some malicious code, a hardware Trojan horse.
So, how do we stop them? Well, modern FPGAs are built like fortresses. First, you can encrypt the bitstream, scrambling it so it's just gibberish to anyone without the key. Second, you can use authentication, basically a digital signature that proves the bitstream is legitimate and hasn't been messed with. And then there's some really cool cutting-edge stuff like PUFs, which use the tiny, random physical imperfections on each chip as a unique fingerprint to lock a design to one specific device.
And that really brings us to the final question to think about. We're all used to the idea of constantly updating our software, but in a world where AI algorithms are changing every month, where new security threats pop up every day, what's the value of being able to update the hardware itself? What does it mean for the future of technology when the silicon is no longer set in stone?